Cool. We are almost at the end of the course content, so this should be the last lecture. Yeah, that's a very good thing. And the other thing is that exam is approaching, so that's yeah, it has both good and bad thing. Since the course is finishing, that's good. Then exam coming. Oh yeah, but again the Christmas is coming, so that's a very good thing. So now you can see that we have the modeling and we know the torque characteristics. Now we want to implement them in the software. Then how we can do that. Before that, I also want to discuss you some phasor diagram or a space vector. If you look at to this, you can see that we write it a space vector diagram. And if you look at the coordinate vector, and we can write this coordinate vector like in the matrix form. Yeah, maybe in the stator oriented system, we can write them as alpha and US beta as a stator coordinate. So we can write them as a coordinate vector like this in the matrix, and we can do all the calculation and everything in the matrix form. Because if you look at the equation there, the machine modeling equation that we have, yeah, here you can see them. So we can do all this thing in the matrix form, like this UX. We can write them as a coordinate vector, and also we can write alternately in the phasor form. So when we did the calculation there, all this thing, and we perform them in the phasor, in the circuit, we can do in the phasor. It's also possible to do all them in the matrix form, like the one that I wrote here. So in the matrix form, it's possible to write. When you write in the matrix form, this means we have one is the alpha axis, and we have one beta axis, or maybe one D axis, or maybe Q axis. So when we develop the control, we usually write the DQ. Yeah, but in this course, we are talking about the alpha K and the beta K. So they are the same. We can do it like this. And if you also write in the phasor, then it is like US, and that is the US alpha S plus J, the complex J, and the US beta. And if you look at also, yeah, and then you have the real axis, and you have the imaginary axis then. So they are more like the same, but different representation. One is the space diagram with a coordinate vector, and another is the complex vector. So you can write here the complex vector, and the other one in the state vector. And then if you look at the diagram, space vector diagram, and you see that it's the rotor field oriented control that we are talking about. This means we have the rotor field here, and the alpha component of the current that giving the rotor field. That's what we have already seen, right? If you remember, psi r, what is? It was xm, yeah, xm is alpha, something like that, I think. So this alpha component was giving us the rotor flux. And then we have the beta component of the current. We have the beta component of the current. This is the beta component. And we see that the beta component of the current, that giving the torque. If you remember the beta component, and if you look at the torque equation, the torque, which is CR IS beta. Yeah. And they are in the rotor field oriented control, so they are in, yeah, K coordinate. Or maybe you can say also one is the Q component, or this one is the D component. Yeah, in some application, you'll see that there one D component and the Q component. So that's what we get here. We have the alpha component. And if you look at the other machine, like this machine, synchronous machine, or the permanent magnet synchronous machine, and we have the rotor. And in the rotor, we are providing separate current to produce the field. But in the induction machine, we don't have anything, right? In the in the rotor. It's just a solid bar. So we need to magnetize the machine, right? If it doesn't have any magnetic field in the rotor, then it will not rotate, it will not produce the torque. So what we are doing, we are providing this current, the alpha component of the current, to magnetize the machine. So same stator current we are using to magnetize the machine, and also we are using same current to produce the torque. So that is the one thing that what we notice here. So if we look at the space vector diagram, then we have the stator alpha component of the stator current in the same direction as the rotor flux, and then we have the beta component here. And also if we look at the voltage, and if we look at the voltage, then it's the 90 degree. Yeah, that's the flux. If you look at the flux, yes, voltage, and which is J f of s psi s. So then we can calculate the voltage vector here, and this voltage vector, it has one small component from the resistor and one small component from the leakage inductor, and then you have this R, and then that's how you can get the stator voltage. So this is the one thing that what we see here. And in order to produce the maximum torque, and we place all the time, we place all the time this 90 degree with respect to the flux vector, rotor flux vector. So you have the rotor flux vector CR here, and then I is beta, which is 90 degree on that. And also, yeah, if you look at the space vector diagram for the stator flux, and you can see this is the stator flux here we have. Yeah, this is the stator flux, this one on the top. And if you look at the voltage, which is the 90 degree, right? If you remember, yeah, from here. Yeah, in this equation, you can see that it has a J in front. And if you scale, this means if you multiply CS with the frequency Fs and put it to 90 degree in the clockwise direction, then that gives you the voltage. So this is the CS. This means you are multiplying CS with Fs and then put this J there. That's how you can get this space vector diagram here. So it's just for understanding how this space vector diagram look like. Yeah, maybe I'll talk the last one. And here you can see that in the previous one, we have the current here. Now we have the current in the other direction, right, here. So we see that still the alpha component of the current, this is the alpha component of the current we are using for magnetizing the machine. And the beta component, this is the beta component, and we are using the beta component to produce the torque, and now the beta component is in the negative direction. This means now it's a braking condition, it's generating instead of acting as a motor. So it's behaving like a generator now. So this is just to present some vector diagram, space vector diagram for you. So in this course, we are talking about a lot the rotor flux oriented control, and then how it comes, the rotor flux oriented control, and it is invented by Felix Plaschke. It's a long time ago. It was in 1969, but that time we don't have this microprocessor, all this thing. So at that time, it was not that straightforward to implement this in the machine drive, because that time we only have the operational amplifier, and we need to do all the arithmetic, mathematical calculation just using the operational amplifier. So it was not that easy that time, but later in the 80s, and we have this digital signal processor, microcontroller, and all this thing, and later we see that this is one of the very good method to control the induction machine, and it's widely used now in industry. So today is one of the very good method to control the induction machine. So it's a quite nice idea, come from long time ago, 1969, and it's doing research it's a doctoral research. So I think it's also very good motivation for you maybe to do PhD, do research, yeah, then maybe you can come up with some new method. And that's how it comes. Some people invent something, and some other people improve it. and in industry, and we are using it. So yeah, that's nice to know. So what we are doing in the rotor flux oriented control, and what we are saying that now we have the alpha k and also the beta k, the neo orientation, and we are also saying that it is rotating with a speed of fs or maybe fk. And when it's rotating, then it's giving us DC quantity. And then we present the model considering a stator current as a state vector, and also rotor flux as a state vector. And also you see that it's a rotor flux oriented control. This means we have only rotor flux in the alpha axis. So it's R, alpha is the total R, and then beta component R beta, which is we see was 0. So from that we got this equation. Yeah, we developed it before. The dynamic equation for the rotor flux. And what you see from this, if you write it like this CR, the derivative term, if you convert into Laplace domain, then you can write this S CR like this. And from this you can write it like if you write the CR, because we are using the alpha component of the current to produce the torque, then you can write that CR which come 1 over STR XM IS alpha. So you have this alpha component there that producing this one, and in the also you see that there is a one transfer function. It's a low pass transfer function, and the time constant for this TR is quite large. So what does that mean? It's quite large. This means even though we can change the current instantly, but it takes time to see the change in the flux. So that's the one thing. Like you can change the current in the current controller very instantly. Like at this point, you change. It's a steep change since you can have the very fast current controller. But if you look at the flux change, then it will be maybe very slow because of this large time constant. So that is the dynamic behavior that what we see. And so in the start of the machine, then we will apply this current, alpha component of the current, to magnetize the machine. And then it's taking a bit longer time to change the flux. Even though we can change the current instantly. And the second equation here, this equation is the steady state equation of the rotor flux. When we put the derivative term to 0, in a steady state, we always put the derivative term 0, because there is no change we are assuming in the steady state. And if you put this term to 0, and you see that steady state rotor flux, which is this magnetizing inductance there, mutual inductance, this value usually 1 to 5 per unit. But some, maybe Roy was saying that he was working on some machine, those has 2 to 4 value of this XM. So, for example, if you want to get the CR like 0.9, we say that when we keep the rotor flux constant, we try to keep it 0.9 or maybe 0.92, not more than that. Because if we have it more, then stator flux become very high and machine can be saturated. So we don't want that. So therefore we keep it something like that. And then to have it like this, maybe if it's 4, then we can have a very small amount of current, like maybe 0.2 or maybe 0.25. So we can use this current to produce the rotor flux, and then remaining current we can use to produce the torque. Because the total current, that what we know, total stator current, which is actually IS alpha square, IS alpha square, and IS beta square. This is the total current. This is the maximum current that we can allow. So the current that we can use for magnetization, and then since we don't need to use that much current for the magnetization, then we can use the remaining current for torque production. So that is the one thing what we see from this equation. And then later, if we also want to see the field weakening and what is happening in the field weakening. Yeah, before that, I also want to say you one thing here is that when you start the machine, then there is no field in the rotor because it's not a magnet; it's a solid bar. So what we can do, we can first supply all the current to magnetize the machine. So we can apply all the current, the maximum current, alpha component, maximum current, to magnetize the machine. Once machine is magnetized, then you can reduce the this current and apply to produce the torque. So you can produce the torque, and you can run the machine. And up to this speed, it run as it is, normal regular operation. But if we want to run the machine higher speed than the nominal speed, then what we can do, we need to do the field weakening. So that's what we can say that if we do the field weakening, then we can run the machine higher speed. And this field weakening is the 1 over inverse, the torque that we are getting. If we reduce the speed, if we increase the speed, then torque is reducing, and it is 1 over inverse. That's what we see here, inverse of the speed. So higher speed and the lower torque, but still we are getting better torque here. What is the reason? Is that we are applying the field weakening. This means we are reducing this current, alpha component, and then we can use the same current also to have the higher beta component of the current. We are reducing here, then we can increase this term, this beta component, to increase the torque. So therefore, we can run it also in the field weakening region and with the good torque component here. If you look at the other machine, then this work very good way here. So any question here? So now we want to implement the controller and how to implement the controller. That in the speed controller, no, in the current controller, we have the current controller here. The first current controller, this would be, this is the current controller. In the current controller, we need to provide current reference, IS alpha and then IS beta. These two current reference we need to give to the current controller. So how can we do that? How can we provide these two current? The beta axis component of the current, we can get it from the torque reference. We have the torque, and we know that torque is equals to CR IS beta. So if we know the torque, and if we divide this with CR, this is the CR, and we are dividing it, that gives us the beta component of the current. So this is the IS beta component of the current. That's how we can get. And we are getting the torque reference here, just providing the torque reference. But we can also implement the outer loop controller, speed controller. Then we provide the speed reference, and then this is the measured speed. And we are providing through a PI controller here, and that can give us the torque reference. So this is the way that how we can, and this is the PI controller that we are discussing in the beginning lecture, and we have this feed forward term, upper limit, lower limit, enable, initial value, all these things. So this is the PI controller that we are talking about. And now we can use the PI controller to control the speed that provide us the torque reference. And when you divide the torque reference with the rotor flux, that gives us the beta component of the speed, beta component of the current. And then how to generate the alpha component of the current? In order to generate the alpha component of the current, we check the C-ref that we want. This is the rotor flux reference that we want. And once we have the rotor flux reference, then we can pass it through a controller. here. This is a flux controller. It's another PI controller. We have the flux reference, and we have also the estimated or measured flux. And then we can calculate the beta component of the alpha component of the current. So that's how we can get. So we have one flux controller. And why we have this flux controller is we are saying that this is a 6-squirrel cage machine, and it doesn't have any magnet, anything in the rotor. So therefore, we need to provide the current to magnetize the machine first. So what we can do before starting the machine, and then we can apply all the current to have the desired flux. This is the current, the blue one, and then I also put this color, green color, for the flux. And once it reaches to this, then we can reduce the current. So if we have the flux controller, what will happen? Then we can apply all the current. This is the alpha component of the current. It's coming through this PI controller. We apply all the current to magnetize the machine, and then it will be much faster. And one is reached to the certain values that we want, then we can reduce the current. Then we have the remaining current to produce the torque. So that's what we can do. Maybe in reality, this magnitude would be maybe even higher. So we can provide all the current to produce to magnetize the machine. So that's the flux controller do. This flux controller. And then the question is how to select this torque rotor flux reference. How to select that? So we can also use a controller, PI controller. This here we have another PI controller. We can use this PI controller to generate this flux. And usually we said that we can put the flux like 0.9 per unit. That's what we said before, maybe 0.9 per unit that we can set. And in the field weakening region, when we do the field weakening region, because we do the field weakening region when we don't have more voltages to have more flux, like stator voltage. Yeah, we know that CS, which is US over F of S. And at certain point, when converter reaches to its limit, then it cannot supply more voltages. If it's not able to supply more voltage, that means we reach to a limit of how much the flux we can supply from the stator here. But speed, we want to have the much higher speed. If it's increased, then we see that this is going down. This is going down. So this means in that case, we need to apply the field weakening. So what we do, we provide the voltage reference here, which is 0.9 per unit. And then is the measured voltage from the DC, like modulation index, which could be like 1, or we also said maybe 1.15. Then what is happening? You can see it's 0.9 minus 1.15. It gives us some negative value. So we are getting negative value, and it comes through this PI controller. So it's reducing the flux reference. Since it's giving the negative value, so it's reducing this flux reference. Instead of 0.9, maybe it gives a little bit lower, so that we can apply the field weakening. So that's how we can select. We can use the outer control loop to have the desired flux for the field weakening, or maybe you can put some fixed flux based on the speed. Like in the next slide that we have here. So as long as it's the regular operation, then you can put it 0.9, something like that. And when we reach the speed limit, and then if we want to still increase the speed, then based on that, we can reduce the reference. And this is how it works in the control. So we can have the lower flux since we want to have the higher speed. This means we are now in the field weakening range. That's what we can do. And it's also possible to set the current reference directly. That's also possible instead of using the additional controller, all this controller, we can directly set this current reference here just by checking that this is the flux that we want, 0.9, and for the 0.9, and then you can calculate this. This is the amount current that we need. So as long as it is this range, the speed lower than the nominal, then you can put it, this is the current. And when the speed is higher than that, and we are now in the field, we can in range, so therefore you need to have a lower flux, lower current. So now if you want to do some simulation, before real implementation, we always do a lot of simulation using different tools like MATLAB, Simulink, other programming, all these things we can do the simulation. So this is one example of implementation in MATLAB Simulink, based on the equation that we develop. So this is the equation that we already developed, and we have the stator current is in the stator current as the state vector, and the rotor flux is the state vector. And we also see that here, this IS, which is IS alpha, plus J of IS beta. And this equation, if you remember, is a stator-oriented control. This is the stator, not a stator-oriented control, it's a stator-oriented frame. This means their sinusoidal quantity in alpha-beta frame. And then we can represent this in terms of the block diagram. So what you can do, like you have this part here in this, and if you apply the Laplace transformation, then you have this S sigma omega 1 SIS is a vector here, and then the right part. And then from that you can write IS, which is 1 over S and omega n S sigma, and what you have in the second part. So you apply the Laplace transformation, you are getting SIS in the first part, and then if you take this part S among X and this part to other side, then you are getting IS, which is 1 over S, this multiply with this, and the rest of the right side part there, this whole right part here. So if you draw them in block diagram, then how it look like? You have the input, stator voltage US. This is the stator voltage US, and how you are getting? You have the three-phase system, this three-phase system, and then we know that how to convert three-phase into two-phase system. And this block diagram we are doing converting three-phase into two-phase system there. And then we have the voltage US there. And then with US, what we see, we have one minus term and one plus term. So therefore, we have one plus term and one minus term. And what you see with the minus term there, this minus term, what you see is RS. RS is equals to, there's a prime. This means it's RS plus RR, both resistor. And then multiply with the current, stator current. So the first part, stator current, come like this. And then, this is the RS prime here. And the second part here, the plus term, is this part. 1 over omega n TR minus J of n multiply with shear. And if you look at all this thing, and you will find like this. So I'm not discussing more detail how, but if you look at, then you will find that this is the implementation in the Simulink, and it is a stator-oriented frame. And one good thing with that, when it's in a stator-oriented frame, then we don't need to think about the magnetization, because it's already in the alpha-beta frame, and we don't need to. And this model is valid for any operation. So that's the one good advantage. You don't need to think about the magnetization. But if you look at the rotor-oriented frame, this is the model in the rotor-oriented frame. In the rotor-oriented frame, we need to provide the magnetization current first to magnetize the machine. because we need to orient it in the alpha axis. Since this is the CR as the alpha axis, we need to first define the angle of that. Yeah, if you remember, which is this is alpha k here. No, it's theta k. And it was alpha s for the stator. So if it is stator oriented, then we don't need any angle information. We just pour it and then we are getting the value. But if we want to have in the rotor orientation, we need to know this angle first. In order to have this angle, we need to provide some current to generate this rotor flux first. So that's the one limitation. If we want to simulate this in Simulink, we need to provide some current first to generate this rotor flux, and then we can simulate it. But if you use the stator-oriented model, then it's valid because we don't need to do any orientation. So this is another way of implementation in Simulink. That's what you can do. Okay. Then now how to implement the controller. Then we see that we can now provide the current reference. Now we need to implement the current controller. So in order to implement the current controller, we can look at the differential equation for the alpha axis and the beta axis current. Why you're saying about the current controller? Because I was discussing in this slide that we now get the current reference, IS alpha reference and IS beta from the outer controller. Now we need to implement the inner loop current controller. So now we are now at the point to implement the current controller. In order to implement the current controller, we need to look at the differential equation of the current, and we see that here we have one alpha component in one beta component in the alpha axis current. We have this alpha axis current, but we have one beta component. So this is the cross coupling term. This means this won't make any disturbance here because of this cross coupling. Similarly, you can also see in the beta axis current, we have one alpha component of current. So you have this alpha component current, and in addition, we have also another two feed-forward term here, these two. So when we implement the current controller, we try always to omit them. So try to do the summation, subtraction, so that they are gone in the final equation. So we have the stator voltage input, and then we have one PI controller. Then we have this cross coupling and the decoupling term, feed-forward term in the second term. This is the PI controller part, and the feed-forward and cross-coupling term. And what we put the feed-forward and cross-coupling term here, opposite sign of that here. So in here, where you see FC here as sigma, IS alpha beta, and you have the plus sign, then you put minus sign. And there you have plus sign, and you put minus sign, so that you can cancel. So if you cancel both of them, then you will get a very nice equation for the differential equation of the current. Now you can see that all the terms, they are gone. Now we have a very nice equation, and they are now a first order differential equation. And if you look at the transfer function of this first order differential equation, and it becomes a very nice equation like this term here. Yeah, something like this. We have a nice first order equation. So now we have this open loop transfer function. We have the first part for the current controller. This is the PI controller. And also we have this delay term that we know, one for the filter and one for the PWM. And one we have this part for the process itself. And one thing we see that we have also DC voltage there. We put a DC voltage because if we supply the converter from a battery, and the battery voltage depends on the charge, state of charge of the battery. So sometimes it goes very high, it goes very low. So when you tune the controller, we also keep it in there so that we can adapt the gain. And now we have the open loop transfer function, and then we can easily apply the modulus optimum criteria to tune the controller. So we are very familiar with the modulus optimum tuning criteria. And then you can apply and you can tune the control. Any question here? Yeah, now we have the final control block there. We have the final control block. Yeah, that's what for the current controller, and we have the current reference that we obtain from the outer loop controller. This is the current controller reference from the current controller, and then we have the D-axis current controller, Q-axis current controller, not D-axis, it's alpha axis controller and the beta axis controller, and then we have this decoupling term that we discuss about this decoupling term. So we are feeding this decoupling term so that they can cancel each other, and then finally we get the first order nicer differential equation. And one thing here, this part, and is the rotor flux model. This means we cannot measure the rotor flux. We can only measure what we can measure in the machine: the terminal voltage, stator terminal voltage, and stator current. These are the things that we measure. Stator voltage we can measure. No, this is a stator current we can measure, and we can also know the speed of the machine. That's what we can only know. So based on that, we need to find a way to calculate the stator flux. And you can easily find the stator flux from the stator equation that, if you already remember, how you can find is dCr dt and minus 1 over Tr is a small t here, Cr plus Xm Tr Is alpha. And if you solve this equation, you have the alpha component of the current, and this Tr is the value depend on the Xm and Xr, that's we know, and then we can get this value. So we can estimate Cr from this equation, right? That's what we can estimate. You can also present it in the block diagram if you'd like. Like if you have the input, stator current input, and the stator current has two components. One is Is alpha and one is Is beta. And this component, if you first multiply with Xm over Tr, a small tr here, a capital T, a small r, and then if you integrate it here, that give you Cr, and again you are taking this back with 1 over Tr, and this is minus sign, right? So this is the block diagram that you can implement in the software, in the Simulink, wherever. So you have only input the current, you have the input current, Is, stator current, that is measurable. And then you have this parameter, they are known. Then you can estimate the rotor flux there. So this is the one way how you can estimate the rotor flux. And then you also need the position of the rotor flux. It's also possible to get the position of the rotor flux. Is the, if you remember the Fs equation, this Fs come with Rr, Is beta, and Cr plus N here. So what you see, you have this beta component, and multiply this beta component. Yeah, multiply this beta component with Rr. Maybe you can put this Rr somewhere here. Multiply this beta component and then divide by this psi r. This is the dividation. And then you add here, this is bit n, and that give you Fs, stator flux. And then if you integrate it, that give you theta, stator flux angle. So this is what you can estimate in the software, in the Simulink. So that's what has been done here. Now we want to see one example implementation, like what you see in the first one. This is the current controller, alpha axis current controller, and we see that the alpha current, this is the reference current, the pink one, and you have the yellow one, the actual, And we apply this, and you see that the current controller tracking very fast the current. But if you look at the flux, it takes very long time. Yeah, because of the delay, that's what we have seen. So therefore, it's taking much longer time to follow the current. And also, if you look at the beta axis component of the current, and yeah, it's quite fast with a small overshoot. Yeah, it's allow, I think 10% is okay there, beta axis component. So the controller works that we apply the method. And also I was saying that it's taking much longer time to follow to have the rotor flux, because the process, the time is delay is much longer, 200-300 milliseconds for the rotor time constant, rotor flux time constant. So it's taking much longer time to reach the reference value like 0.9. Even though we provide the current here, but taking much longer time to reach there because of the delay that we have already seen there. While the Q-axis component, beta axis component, it follows, and this means it follows the torque very efficiently. And in here, I also want to show you this phasor plot, XY plot, and what you see there. We apply first the alpha axis component of current here. And this is the alpha axis component of the current that we apply. Only the alpha axis component of the current. So what you see when you apply the alpha axis component of the current, then if you look at the rotor flux, and the rotor flux taking some time, and it reaches to this. So you got the CR there. So once it reaches there, now we magnetize the machine. So this is the condition where we magnetize the machine, and then we apply the d-axis current, not d-axis, beta-axis current to produce torque. So now we provide this beta-axis component, then we have the current vector like this, because now we apply the beta-axis component of the current. When you apply the beta-axis component of the current, and you see that machine starts rotating. So when you apply torque, and then machine starts rotating, and also we see that this component there in the rotating, they are also rotating this current vector. And one thing is that we have here an angle theta or something like that. This is the angle. So this angle is always forward. So when this CR, it comes to this position, like for example, here came to in this position, this means rotor current vector, it come to this position, because it's always maintain the phase different, the angle that it initially has. Initially when it was 0, and then you see that it has this angle, something like this angle delta. So when it come to this, then you if we CR come to at this position, then the current has here the current vector. So this is now rotating. Any question here? Yeah, I just want to present to you one of the thing here. When you implement the control, and what you see when you implement the control, in the beginning, that we see that in the beginning here, this is the alpha axis component of current, this one, and the beta axis component of the current. And we keep the alpha axis component is the high value as possible to magnetize the machine, and we put the beta axis component current is 0, and then we are magnetizing the machine here. So you can see the flux of the rotor is increasing, and when it reaches to the value that we want, then we can apply the beta axis component of current, and then we apply the beta axis component of current, and then machine starts rotating. So that's what we see. Yeah, and also here I just want to present that we say that we can have a lot of ripple in the current, and then we apply the synchronized sampling